We are going to understand theorem 1.5, 1.6 and 1.7 using some examples. So theorem 1.5 says that let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q, where p and q are co-prime, and the prime factorization of q is in the form of 2n 5 raised to m, where n and m are non-negative integers. So if you can understand, the prime factorization will have 2's and 5's and power 2 raised to any power and 5 raised to any power, but they have to be non-negative. That means they could be 0 or positive numbers. So let's understand what's given to us. It's given that x is a rational number, and it is also given that the decimal expansion of x is terminating. The conclusion is, if the decimal expansion of x is terminating, then q will be in the form of m, 2 raised to n, 5 raised to m. So let us take a terminating decimal expansion, which is 0.375. Now, if you want to write it as a rational number, since it's a rational number, we will write it as 375 upon 10 cube, because there are 3 digits after the decimal point. Now we need to make p and q co-prime, so we will remove all the common factors from p and q and check the prime factorization of q. So after making them co-prime, we will check the prime factorization of denominator. So let's prime factorize them. Now 375, when you divide it by 5, you get 75. Again by 5, you get 15, 5, 3, 3, 1. And 1000 prime factorization is 2. If you divide by 2, you have 500, 2, then 250, again with 2, 125, again with 5, 25, 5, 5, 5, 1. And so we can write it as 375 as 3 into 5 cube and 1000 as 2 cube into 5 cube. Now, because we want to make p and q co-primes, we will remove the common factors. So 5 cube and 5 cube are cancelled out, and so what we have is 3 upon 2 cube, which is co-prime, since there are no common factors left. Now let us check the prime factorization of q. Is it in the form of 2n 5 raised to m? Yes. Though we don't see 5 as a factor and it has been cancelled out, we can say it is 2 raised to 3 into 5 raised to 0. And so it is in the form of 2n 5 raised to m. And so since the decimal expansion of 0.375 is terminating, we can see that q is in the form of 2 raised to n 5 raised to m. Let us take another example. Now the decimal expansion is terminating. It ends at 4, 0.104. It can be written as 104 upon 10 cube. We need to first make p and q co-primes, so we will prime factorize them. 104's prime factorization will give us 2 cube into 13, and you already know 10 cube will be 2 cube into 5 cube. In this case, 2 cube will cancel out, and so the co-prime form of this decimal expansion is 13 upon 5 cube. Now, is the denominator here in the form of 2 raised to n 5 raised to m? Again, yes. Though 2 raised to 3 has been cancelled out, actually it has turned 0. So we have 2 raised to 0 into 5 raised to 3. And so we can say that since the decimal expansion was terminating, we have the denominator in the form of 2n 5 raised to n. So the theorem stands true. We will take one more example. it is 0.0875, and since there are 4 digits after the decimal point, the p by q form will be 875 upon 10 raised to 4. And now let us prime factorize 875, and we will get 5 cube into 7, and 10 raised to 4 becomes 5 raised to 4 into 2 raised to 4. Now here you can see we have 5 cube and 5 raised to 4 here. So we will cancel out all the 3 5s from the numerator. From the denominator, 1 5 will be left. So we will have 5 raised to 1 left. And so you can see the final p by q form, which is the co-prime form, will be 7 upon 2 raised to 4 into 5 raised to 1. Is the denominator in the form of 2 raised to n, 5 raised to m? Yes, here in this case, we have it as 2 raised to 4 into 5 raised to 1. It is. So you can conclude that when the decimal expansion is terminating, the prime factorization of the denominator will be in the form of 2 raised to n, 5 raised to m. Now, theorem 1.6 tells us the opposite. It's the converse of the previous theorem. Here it says let x be p by q, that means it's a rational number, such that prime factorization of q is of the form 2m 5 raised to 2 raised to m 5 raised to n. That means that q is, we already know that q has a prime factorization of this form, where n and m are non-negative integers. Now we need to conclude that x has a decimal expansion which terminates. So let's understand what's given to us. It is given that x is in the form of p by q, it's a rational number, and q is in the form of 2 raised to n, 5 raised to m. The conclusion is the decimal expansion of the x will be terminating. So let's take an example and understand. Let's take 3 divided by 8. So it can be written as 3 upon 2 cube. Now the prime factorization of the denominator is in the form of 2 raised to n, 5 raised to m, correct? Though 5 is raised to 0 here, but it is still in this form. Therefore, we can conclude that the decimal expansion will be terminating. Let's check out. So to make the denominator into base of 10, we will multiply 5 cube and 5 cube in the denominator and the numerator. So 2 cube into 5 cube, here we get 10 cube, and 3 into 5 cube becomes 3 into 125, and that will make it 375 upon 10 cube. And you can see we get a terminating decimal expansion, 0.375. Let's take another example, 13 upon 125. Now, it can be written as 13 upon 5 cube. Again, the denominator is in the form of 2 raised to n, 2 raised to 0 into 5 raised to 3 in this case. And therefore, I can conclude without even calculating and getting the decimal expansion that the decimal expansion will be terminating, because I can make the denominator in the base of 10 by multiplying 2 cube and 2 cube in the numerator and the denominator. So this becomes 13 into 8, which gives us 104, and this will become 10 cube. And so we have 104 upon 1000, which will give us 0.104. And as you can see, the decimal expansion is terminating. Let's take one more example. 7 upon 80. Now it can be written as 7 upon 2 raised to 4 into 5. This is the prime factorization of 80. And it is in the form of 2 raised to n, 5 raised to m. Here 5 has the power of 1. Now what do I need to multiply to the numerator and denominator to get a base of 10? Since 2 is raised to 4, I want to make it 10 raised to 4. So 1 5 is already there. I need 5 cube. I need to multiply 5 cube here so that it becomes 5 raised to 4. And I will also multiply 5 cube in the numerator. So this is 7 into 125. And this is 2 raised to 4 into 5 raised to 4. This will become 5 raised to 4 to make it 10 raised to 4. Okay. So we multiply 5 cube. This will give us 875, and 2 raised to 4 into 5 raised to 4 gives us 10 raised to 4. And so 875 divided by 10,000 now gives us 0.0875. Again, it's terminating. So when you know that the denominator is in this form, we can definitely conclude that the rational number will have a terminating decimal expansion. Now, the next theorem is theorem 1.7. It says that if x is a rational number in the form of p by q, such that the prime factorization of q, we know that the prime factorization of q is not in the form of 2 raised to n, 5 raised to n. That means there are other factors here, apart from 2 and 5, where n and m are non-negative integers. Then what is the conclusion? X has a decimal expansion. It will have a decimal expansion, but the expansion will be non-terminating. That means it will continue. And there will be a repeating string. That means after a certain time, the strings will repeat itself. Okay? Remember, it is a rational number, but only that the q is not in the form of 2 raised to n, 5 raised to m. The only difference is that. So here it is given that form of p upon q, and p and q are co-primes. Q is not in the form of 2 raised to n, 5 raised to n. You can see it is not equal to this form. Then we conclude that the decimal expansion of x will be non-terminating and recurring. Okay. Now let's take an example. Let's divide 1 upon 7. So if you look at this rational number 1 upon 7, you can see that 7 is not in the form of 2 raised to n, 5 raised to m. And so let's start and divide it and see. We will have to put a 0 here, so we get a decimal point. 7 ones are 7. 10 minus 7 gives us 3. We will put another 0 here and bring it down. So this becomes 30. 7 fours are 28. 30 minus 28 gives us 20. We will have to put another 0 here and bring it down. So this becomes 20. 7 twos are 14. 20 minus 14 gives us 6. We will put another 0 and bring it down. This becomes 60. 7 eights are 56. You will get 60 minus 56 is 4, and we put a 0 and bring it down. So we have 40 here. 7 fives are 35. 40 minus 35 gives you 5. We will put another 0 and bring it all the way down. So we have 50. 7 sevens are 49. And then we have 1. Again, we will continue. Since you will see that it continues now, we will put 0 here, and bring it down. So we get 10, and this string of numbers will repeat, because now we will say 7 ones are 7, and again it will be 10 minus 7, 3, 30 minus 28, 2. Then it will repeat, the string will repeat itself. 142857, 142857. So you can see it is non-terminating. It is not going to terminate. So we have it as non-terminating, and it will repeat. This string is going to repeat itself. And so we say it is recurring. This happens only when the rational number's denominator is not in the form of 2 raised to n, 5 raised to m. So as you can see, 7 is not in the form of 2 raised to n, 5 raised to m. the decimal expansion is non-terminating and recurring. If you take a rational number 1 upon 6, 6 also, if you see the prime factorization, it is also not in the form of 2 raised to n, 5 raised to m. And so I can conclude that 1 upon 6 will also have a non-terminating recurring decimal expansion. You can try it on your own.